Hello, and welcome to episode 3 of the Kalopa Mission Control Podcast. I am your host, and it is a profound pleasure to have you join me once again as we look out across the great grey expanse of our world's oceans. Whether you are listening to this with a cup of warm tea while the rain lashes against your window pane, or perhaps walking along a quiet stretch of coastline, taking in the scent of salt and seaweed, I invite you to settle in. Here at Kalopa Robotics, we spend our days designing, building and tracking autonomous robotic sailing vessels. But before we are engineers or programmers or data analysts, we are fundamentally students of the sea. As an oceanographer, I have spent the better part of my life staring out at the horizon, trying to comprehend the sheer unfathomable scale of the marine world. It is an environment of stark contrasts. It is capable of terrifying violence, yet it is also the cradle of all life on Earth, possessing a fragile, intricate balance that we are only just beginning to truly understand. Far below the surface, on the abyssal plains of regions like the Clarion-Clipperton Zone in the Pacific, lie scattered deposits of polymetallic nodules. These potato-sized formations, which take millions of years to grow, are rich in nickel, cobalt, copper and manganese, minerals that are currently in high demand for electric vehicle batteries and renewable energy infrastructure. However, recent scientific expeditions have revealed that these nodules do far more than just sit in the dark. They are involved in complex electrochemical processes that actually generate oxygen in the deep ocean, completely independent of sunlight and photosynthesis. It is a discovery that has turned our understanding of deep sea biology entirely on its head. To send massive robotic vacuums down to strip mine, these nodules would not only generate sediment plumes that could suffocate midwater species and disrupt tuna migrations, but it could fundamentally alter the oxygen cycle of the deep sea. The High Seas Treaty now mandates rigorous environmental impact assessments for such activities. It demands that we look before we leap and that we recognise the deep ocean not as a barren quarry, but as a living, breathing ecosystem. And what an ecosystem it is. Just recently, a UK-led scientific expedition aboard the research vessel James Cook returned from the Caribbean with footage that seems lifted straight from the pages of a science fiction novel. Mapping the previously uncharted waters around the Cayman Islands, Anguilla and the Turks and Caicos, they discovered a towering underwater mountain called Picklebank, adorned with golden coral towers and orange sea sponges. Even more astonishingly, they located a massive vertical blue hole, a collapsed underwater cave, dropping 550 meters below sea level. Within these depths, they documented hundreds of species, including a pelican eel with a glowing pink tail that flashes red to lure its prey, and a bizarre, alien-like barrel-eye fish whose tubular eyes point straight upward through a transparent dome on its head to spot the silhouettes of prey against the faint surface light. It is a wonderful, humbling reminder that we know more about the surface of the moon than we do about the floor of our own ocean. This interconnectedness of marine life means that protecting the high seas has profound ripple effects all the way to our coastlines. Consider the African penguins of South Africa, a critically endangered species whose numbers have plummeted due to food scarcity and shifting ocean currents. Recent tracking data has shown that in years where fish stocks are low, these penguins are forced to forage in the exact same waters used by commercial purse-seine fishing fleets. By mapping these overlapping zones, conservationists and policymakers are now designing dynamic, highly targeted no-fishing zones around breeding colonies like Robben Island, giving the penguins a fighting chance to rear their chicks. Similarly, off the coast of California, there is a renewed push to expand marine protected areas to save the last remaining kelp forests. These magnificent underwater cathedrals of giant kelp and bull kelp provide sanctuary for an incredible diversity of life. They have been severely degraded by marine heat waves and an explosion of purple sea urchins. Protecting these areas from further human extraction allows the natural balance of predators and prey to re-establish itself, proving that when we give nature a moment of respite, she is remarkably adept at healing herself. It is into this vast, complex and newly protected global ocean that we at Kalopa send our robotic emissaries. Now, turning to our own fleet. If you are looking at the Kalopa Mission Control dashboard today, you will notice that the screens are rather quiet. We do not currently have any active missions out on the water. Our boats are safely tucked away in the workshop, undergoing maintenance, upgrades, and a fair bit of tinkering. When the telemetry screens are dark, it affords us a rare and welcome opportunity to step back from the raw data, the wind speeds, the battery voltages, the GPS coordinates, and talk a little bit about the philosophy of what we do and the remarkable little machines that make it possible. Our vessels are 2.4 metre autonomous surface vehicles, or ASVs. 2.4 metres. That is just under 8 feet long. If you were to lay one out on the floor of your living room, it would barely stretch from the sofa to the television. And yet we ask these tiny, fragile constructs of fiberglass, carbon fibre and marine-grade aluminium to survive in the most hostile, unforgiving environment on planet Earth. Designing a boat of this size for the open ocean is an exercise in extreme humility. You cannot overpower the sea. A traditional crewed vessel might use massive diesel engines to punch through a rising swell or rely on the seasoned intuition of a human captain to steer out of a breaking wave. A 2.4 metre robotic boat has no such luxuries. It relies entirely on the wind for its propulsion and the sun for its electrical power. When a North Atlantic gale whips the sea into 10-metre swells, our little boats do not fight the ocean. They submit to it. They are designed to be self-righting. If a rogue wave catches the hull broadside and rolls the boat entirely upside down, plunging the mast deep underwater, the heavy lead bulb at the bottom of the keel acts as a counterweight, swinging the vessel back upright within seconds. It is a violent, dizzying piece of physics, but it is absolutely essential for survival. The onboard computers, the brains of the operation, must be sealed in completely watertight compartments. They are constantly reading data from wind vanes, compasses and GPS units, calculating the optimal angle for the sail and the precise adjustment of the rudder. All of this must be done while sipping power, drawing only a few watts of electricity so that the onboard batteries can survive the long, dark nights when the solar panels are useless. Why do we build them to exactly 2.4 metres? Well, aside from being a highly efficient size for testing and deployment, it happens to be the maximum allowable length for the Microtransat challenge. For those who may be unfamiliar with it, the Microtransat challenge is, quite simply, the Everest of robotic sailing. It is an ongoing transatlantic race for autonomous boats aimed at stimulating the development of marine robotics through friendly, albeit fiercely difficult competition. The concept was born in 2005, formulated by researchers Mark Neal and Colin Sawes. The premise is beautifully simple. Build a fully autonomous boat, launch it from the coast of Europe or North America, and have it cross the Atlantic Ocean without any human intervention. No remote control, no chase boats, no repairs. Once it leaves the shore, it is entirely on its own. There are two routes. The westbound route challenges teams to sail from the coast of Europe, typically Ireland or France, down past the Canary Islands and across to the Caribbean or the Americas. The eastbound route, which is arguably much rougher, requires boats to launch from the eastern seaboard of North America, usually Canada or the United States, and ride the prevailing westerlies and the Gulf Stream toward the western shores of Europe. To say the Microtransat has a rich and varied history would be a magnificent understatement. For over a decade, the Atlantic Ocean proved to be an impenetrable fortress. Year after year, brilliant teams of university students, naval architects, and retired engineers would bring their bespoke creations to the shoreline. They would launch them with great fanfare, watch them sail bravely over the horizon, and then, invariably, wait for the inevitable silence. The ocean, you see, is incredibly inventive when it comes to destroying small robots. Some boats were caught in massive circular eddies, sailing in endless loops until their electronics succumbed to the damp. Others fell victim to biofouling. In the nutrient-rich waters of the open ocean, a clean hull can quickly become a floating reef. Barnacles and gooseneck mollusks would attach themselves to the rudders of competing boats, growing so thick and heavy that the steering mechanisms would jam entirely. We have even seen telemetry data suggesting that boats were scooped up in the nets of passing fishing trawlers, or, in one memorable instance, likely attacked by a curious shark that decided the boat's underwater hydrophone looked like a tasty snack. It wasn't until 2018 that the Norwegian team Sailboy finally conquered the eastbound route, their vessel washing ashore in Ireland after months at sea. It was a triumphant moment that proved it could be done, and it reinvigorated the entire community. The beauty of the Microtransat challenge is not just in the crossing itself, but in the community it fosters. When you look at the roster of teams that have attempted it, you see a brilliant cross-section of humanity. You have well-funded university labs with access to aerospace-grade materials and wind tunnels. And right next to them on the starting list, you have a group of primary school children who have built a boat out of plywood and determination, tracking its progress on a classroom whiteboard. There is a profound, almost poetic romance to it in an age where we can instantly video call someone on the other side of the planet or track a parcel to our doorstep with pinpoint accuracy. There is something deeply grounding about placing a small mechanical Voyager into the surf, letting go, and trusting it to the wind and the waves. Every time a team launches a boat, they are participating in a dialogue with the ocean. The telemetry we receive, the slow, steady drip of coordinates and sensor readings, tells a story of survival. The winds picked up to 18 knots from the southwest today, the data whispers, which pushed the boat into a beautiful broad reach. Or perhaps the solar array was shaded by heavy storm clouds for 3 days, but the power management system successfully put the steering to sleep to conserve the battery. These are the stories we live for at Kalopa. Our 2.4 metre boats are standing on the shoulders of all those who have braved the Microtransat before us. We learn from the lost rudders, the waterlogged circuits, and the barnacle-encrusted hulls. Every failure in robotic sailing is simply a data point, teaching us how to build a better, more resilient vessel for the future. And as the High Seas Treaty begins to cast a protective net over the vast open ocean, the role of these autonomous vessels becomes even more crucial. We cannot protect what we do not understand, and we cannot understand an environment as vast as the ocean without a fleet of silent, non-invasive observers. Our autonomous boats do not require diesel fuel. They do not drop anchors on fragile coral reefs. They do not leave a wake of noise pollution to disorient passing whales. They slip through the water as quietly as a fallen leaf, observing, measuring, and reporting back. They are the perfect tools for this new era of ocean stewardship. As we look ahead, the team at Kalopa is busy preparing for our next deployment. The workshop smells of marine epoxy and soldering iron flux, the perfume of progress. We are taking the lessons learned from our previous missions, refining our weather routing algorithms, and ensuring that our next vessel is as prepared as it can possibly be for the wild, unpredictable theatre of the open sea. We will, of course, bring you all the updates as soon as our hull touches the water and the sails catch the wind. But for now, we must be patient. The ocean has operated on its own majestic timetable for billions of years, and it certainly will not be rushed by us. Thank you for joining me for this episode. If you share our fascination with maritime engineering, oceanography, and the quiet thrill of autonomous exploration, please do subscribe to the podcast on whatever platform you happen to be using. It is a joy to share these stories with you. Until next time, keep your eyes on the horizon and take care. Goodbye for now.